So while we are waiting, if are there any questions, like in general about the course, about the lab? Okay, if not, what we will do, I will switch on the recording. Can any one of you switch on the recording, because I'm not from the right tenant, I'm joining from my Microsoft account. Okay, thank you. And I assume you can see my screen, right?
Yes, you can.
Thank you. So what I suggest we do, we'll talk today about implementation of functional programming languages. And I hope you excuse my Russian slides, but I will speak in English. And this topic will also include a little bit information about parsing, which is relevant for Lab 3. Some of you asked me, like, what's the best way to convert text into internal representation, and that is something which is very important for implementation of programming languages, because when we start implementing a programming language, we are having the same problem. We start with plain text. Sorry, and this plain text. Just give me a second. I will. So when we start implementing programming language, we start with plain text, and we convert this plain text into something, into some internal representation, which is called abstract syntax tree. That is what normally happens. And when we are talking about functional programming languages, this syntax tree can be considered as some kind of lambda calculus extended with some additional things like primitive functions and maybe let construct and so on. And then once we have this internal representation, we can do different things. The most traditional thing is to interpret this tree directly, and that is what was done in the first functional programming language, Lisp. In Lisp, the program was very close itself to the abstract syntax tree, and that's why the interpreter was kind of built into the system naturally. And we will talk today how this interpretation can work. If we want to do something like lazy programming language, we can do graph reduction, or we can translate this into some kind of abstract machine and then interpret this code. And that is the approach which is close to F#, because F# converts the program into .NET abstract machine code, and it is then interpreted to get the result. And I will not go into details into things like JIT compilation and so on. And for abstract machines, there are also different alternatives like categorical abstract machine, SECD, sect machine, which we will talk about today, and so on. So how would we do this? Like let's see how can we implement this thing. And start with this direct interpretation. So what we want to do, we want to have a kind of lambda expression and write an interpreter which will evaluate this expression. And if you remember, in lambda calculus, we are talking about reduction. So we have like a program which is a large lambda expression, and we want to make it smaller and smaller until we get the result of the program. So if we want to write this kind of interpreter in F#, we would need to represent the lambda expression somehow. And this can be done exactly in the same way as you are representing in your lab, as you're representing structured text. Because lambda expression, like what is a lambda expression? We know that lambda expression consists of two basic operations, application and abstractions. So we can say that lambda expression can be application of two expressions, or it can be abstraction, which I will call lambda of. And if it's an abstraction, we need to specify a variable on which we are abstracting and another expression, right? So this is the basic structure which allows us to represent lambda expressions in F#. If we want this to be practical, of course, we also want to include here things like if we want expression to also be represented not as text but as some structured thing. So expression can be a variable, in which case it would be like var with a name, or it can be a constant. And for simplicity, I will assume we are only dealing with integers. So let's say it would be int of int. And that would be pretty much it. But I also want things like functions, primary functions like plus, minus, and so on. And for that, I will include one more thing like pfunc. I would call it, it would be a primitive function and let it be of string so that I write plus, minus, or things like that. So if I want to write an expression 2 plus 2 using this language, I would say 2 plus 2 is an application of plus to numbers 2 and 2. So I would say up, and then the first application would be pfunc of plus and int of 2. Then the second application int of 2. And that would be 2 plus 2 using this internal representation of our small lambda calculus. However, if we want then to interpret this, to write simplifier for this lambda expressions, we would probably need to add some more things to this definition. So I will take the existing definition which I have here in this example, and I will share this example with you so that you can play with it later on. We have pretty much the same things as I have already demonstrated. Then, because we are talking about eager programming language, we need some separate implementation for conditional, for if operator, so that we don't evaluate both parts of that. We cannot implement conditional as the normal lambda expression because it would be eagerly evaluated. That's why we do separate operator for if, which is cond. And then I will also use let separately. I will define it as a separate type of node. The reason I do that is to make things more effective, because of course let can be implemented using lambda expressions, but because let is a very important part of the language, it's more efficient to implement it separately. So I would have let, and I would also have let rec for recursive version of let, and then I would need two more things. I would need intermediate node called op, and the reason I need this op is that if I want to implement, for example, 2 plus 2, it is evaluated in two steps. It is first, as we've seen before, it's like application of plus to 2, and then another application to 2. So if I want to do that properly, I need to somehow this plus is not applied immediately, right? It is first applied to first two, and then this partially evaluated plus can be applied to something else. So of course, all partial evaluation with lambda expression happens automatically, but if I want to this partially apply primitive functions, I need to store this partially applied plus. So exactly for this, I need this op clause, and it will store the operation itself, ID, which would be plus. It will store the number of arguments which we need to supply before it's completely evaluated, and it will store the list of arguments which has been so far evaluated. So this is the op thing. And then we also need a separate thing for closure. I remind you that closure is when I have the when I have some lambda expression which I want to like name as a function which contains external variables. I need to fix the value of those external variables so that later on they will be substituted by their previous value. So this is called closure, and we need two versions of closure for normal closure and the closure special closure for recursion, and that we'll see later why we need it. So this is the expression type, and also for closures, you see that closure is the tuple of expression and environment. Environment is the mapping from variable names to expressions. It is the current list of assignments. So exactly that we need for closure, right? We need the function which we need to evaluate and the list of current values of all variables, which is environment. And environment I will represent as a map from ID, from string essentially, to expression. So that is our types. Those are types which we will use. And then the first, the simplest version of interpreter is called eval apply interpreter. So here again we have this 2 plus 2, 8 plus 2. Then I will define a couple of useful functions, like in order to support operators with any other number of variables, I will introduce this arity function. But in our case, we will only consider plus, minus, and multiplication and division. So essentially, all our operators would be primitive operators would be binary. But just in case we want later to put something else, I will introduce this arity function. Then there would be one more function which is called funoff, which will build from the name of the operator, from plus, from minus, and so on. It will build a function that does the computation on the list of arguments. So, for example, for plus, it will take the list of int a and int b and produce int of a plus b. Int is our name for integer. Remember, in this here we defined like this int of something. So it's the internal representation for integer. So it will build a function which operates on those internal representations. And I will also build functions for comparison, like, because if we want to implement something interesting like factorial, we would need to be able to compare things. Now for the main interpreter. So main interpreter consists of two mutually recursive functions. So this is the main interpreter. It's not too big. And it is called eval apply interpreter. It is the traditionally something which was implemented in Lisp. This approach with two mutually recursive functions. So two functions are eval and apply. Eval is the main one. It will evaluate any expression in a given environment. Environment is a mapping from names to variables, from variable names to values. So how do we define it? Let's, of course, it needs to break down the expression according to all possibilities in the expression tree, right? So what can expression tree be like? It can be apply, in which case it is simple. I will just call apply function. So apply function is exclusively for doing application. So it will essentially do a step of beta reduction. And here, before calling this apply, I do eval on both arguments, because what can happen when I want to evaluate an application, the parameters of application can be anything. It can be arbitrary lambda expression. It can be, for example, primary function. If I want to call 2 plus 2 squared, I want to apply this function square to 2 plus 2, I need to evaluate 2 plus 2 first. So this is where this evaluation happens. So I evaluate both E1 and E2 in the given environment, and then I pass the evaluated things to apply. So if I have integer, of course, I return integer. If I have variable x, what I need to do to compute, to evaluate it, I find this variable inside the environment and return the value. So that's pretty simple. This is the simplified version, of course, because I do not check if the variable exists, and I do not say what I need to do if it doesn't exist, but presumably it will just do the exception or something like that. Then how do I evaluate pfunc? If I see plus, I replace it by this op notation. So I say it's op of this plus, then arity of f, so it would be 2 initially, and the empty list of arguments. Then the op is intact. If I see a conditional operator, what I do, I evaluate this E0, the condition. If it's 1, in this case, I consider 1 to be true and everything else to be false, just for simplicity, but we can go any other way. If it's true, then I evaluate E1, otherwise I evaluate E2. That's pretty obvious. Then what I do if I see let. If I see let x equals something so here this let with 3 arguments means let this ID. So yeah, let me write it as comment here. So it means let ID equals E1 in E2. So I need to substitute ID for E1 inside the expression E2. So to do that, what I do, I evaluate E1 because it can be an expression, and then I add this to environment, right? I add ID to environment, and I evaluate E2 in the extended environment, which contains also this variable ID. I will skip the recursion, and finally, another important thing is lambda. When I see lambda, I turn it into closure. So the most obvious thing is the beta reduction when I have lambda expression and I apply it to something. So what happens here is that eval turns lambda into closure, which captures the environment and evaluates the argument, and then calls apply, right? That's what we've seen here. So it evaluates both parts and calls apply. And if the first part is lambda, it converts it into closure. So apply function, what it will get as input, it will get always closures. It will never get lambdas. And closures, they have the environment. So normally, the normal beta reduction would look like this. I would have, I evaluate this function on E1 first. So I would have closure as the first parameter. So closure can be lambda VE in the environment env. So what do I need to apply this to expression E2? Essentially, I need to evaluate expression E. So the expression inside lambda. In the extended environment, right? I add this variable v with the value of e2 into the environment original, and I evaluate e in this extended environment. So this is how application happens. And I will skip the recursion for now. And the second possibility is the primary operation. So if I want to apply, I can only apply either closure to something, or I can apply primary operation. So for example, if I want to apply plus to 2, what needs to happen? If I see that the remaining number of arguments is 1, which means that I am applying it like it's the final application. I don't need to expect any more arguments. Then I just convert this ID into function and apply it to the list of accumulated arguments plus the one that I have received now, E2. Otherwise, I just accumulate. So I replace the previous op by op with one less arguments to expect, and I append this E2 to the list of arguments. This is not the most effective implementation, by the way, because I append to the end of the list. I don't know why I'm doing that. Probably just because was not optimized. Normally, I should prepend this E2 to the beginning of the list, and I should change the fun off into reverse order of arguments, but to make things more effective. But let it stay like this. Okay, let's see how it works. So I will call E of expression. It would be a val of exp with the empty map. So I can just say E of something and get the value. So let's see the example. And you have noticed maybe that I have included here the print operator so that we can see what goes on. This is slightly old version of F#, so I can simplify it a little bit. Okay, so this is the first thing, 8 plus 2. How would it be evaluated? Let's have a look. So 8 plus 2, it first evaluates application of plus to 8, right? Then it evaluates both sub-expressions, so it tries to evaluate plus and returns op. It tries to evaluate 8 and returns 8. So this is the first result of evaluation, op plus 2 and empty list, and 8. So now it needs to apply this op to 8. And the way op is applied, it is converted into this op. Op plus 1 and then 8 is a list of arguments. And then I need to apply it to 2. When I apply it to 2, this part of op evaluation happens, and I actually evaluate this and return 10. This is pretty simple. Now, something a little bit more complicated. Let's see lambda xx applied to 5. So it should return 5, but we would see how lambda expressions are evaluated. So I want to evaluate lambda xx applied to 5. I evaluate both parts of the expression, and lambda xx is converted to closure. So I am left with this lambda xx with empty map, and I want to apply it to 5. When I apply it to 5, what happens is that I insert this x equals to 5 into the environment, and I evaluate this variable x, right? So that is exactly what happens here. I want to evaluate variable x with map of x corresponding to int 5. And now this place here happens. I find this x in the environment and I return 5. Okay, something more complicated. I want to evaluate x plus 1, lambda x plus 1, and apply it to 5 to get 6. So this combines previous two evaluations. So how this happens? First of all, the same thing as before. We evaluate. First of all, we evaluate this lambda x x plus 1, and it is converted into closure, and we want to apply it to 5. So to do that, we insert x equals to 5 into the map, and then what happens is the evaluation of this lambda x x plus 1 exactly in the same way as we evaluated 8 plus 2 before, but we have in the environment we have x corresponds to 5. So that means that whenever we see instead of integer we see variable x, this variable x will be replaced by the value, and at the end we'll get 6. So that's how it works. And here is a little bit more complicated example when we have a few variables. So this let id equals to lambda xx, let square equals to z times z. So lambda z times z, and then I evaluate square of id of 5. So this should give me 25 in the end. And we can just see that indeed it gives me, it is a little bit more complicated evaluation, but at the end it gives me 25. So this was eval apply interpreter. Now let's try to see what happens if we want a recursion. So if we want a recursion, what I need to do essentially, like why I cannot use let for recursion, because when I do the evaluation, I only insert the value of the function into the map, and it can be so inside the definition of the function, the name of the function does not exist, right? So when I do let, I say let id e1 equals e2. So I add the name of the function e1 is not added to the environment. So if I want to implement recursion, I need the name of the function to exist in the context in the environment of the function itself. So that's why I need a separate let for recursive definitions. And the difference here is that I also do eval e2, but to the environment to the environment where a function is evaluated, I insert this name of the function, and for the name of the function, I insert r-closure, and I store here. Pretty much, it's the same as closure, but I also need the function name to reinsert it again during the recursive call. So it's the same as closure. I store the e1, so the function itself, the whole definition of the function, the current environment, and I also store the name of the function here. So if I evaluate factorial, for example, this would be e1 would be the body, env would be the current environment, and id would be the name fact. So then when I evaluate the function, what can happen is that when I use the name fact in the right-hand side in the definition of the function, it will give me this r-closure. So I would need, sorry, I would need to treat this almost in the same way as the normal closure, but I would need to reinsert the name of this factorial into the environment again. So if I evaluate the factorial inside the factorial, I want in this next level of recursive call, I want the name fact to also be available. So that's why it's this handling of our closure is the same as handling of normal closure, but it adds again the definition of the function to the environment. So that's where it happens. I insert pretty much the same R closure into the environment again. So that is how we can handle recursion. So now with these recursive things, we can define things like factorial. So this is the definition of factorial. I'll say factorial is lambda x, then condition if less or equal x to 1, I return 1. Otherwise, I return multiplication of x by factorial of minus x1. And then I apply this factorial to 5. So this will calculate factorial of 5. Let me see if it happens. Yeah, it gives me 120 at the end. So that's pretty much how functional programming languages are implemented. So what we have already done now, we have specified this kind of internal representation for functional programs containing only numbers and simple operations, but we can write any programs like any functions like factorial using this notation, which is kind of cool. Now, what we want to do if we want to make this a lazy interpreter. So if you want, so why this is not lazy? It is not lazy because when we do application here, we evaluate both parts of the expression, right? So that's why it's eager. If we want it to be lazy, we don't want to evaluate the arguments, right? So we will introduce the special construction for evaluation, for suspending evaluation, which we will call susp. And susp is pretty much like closure. In fact, it can be completely, like it can be used, the closure can be used instead of susp. I just use susp to make it a little bit more clear, like why do we have it here. So what it does, it captures the current argument and the environment, and it evaluates it later on. So that is pretty much the lazy evaluation. And why is it almost the same as closure? Because in the eager programming languages, you know, we can make an expression explicitly lazy by replacing it with a function with no arguments, right? So if I say fun without arguments, which computes the expression, it is the same way as I delay the computation of this expression, and then later on I can call this function to get the value. So, and if we define this function without arguments, it will be replaced by closure. And so that is why this susp is the same as closure. So during application, we just suspend the computation of the second argument, and inside let we also suspend the inside the let. In this case, we will get suspended arguments, right? So inside let we will also suspend the computation of Ivan. So we'll put this into the environment. And then, of course, we also need to handle things like plus separately. So for plus, we would also need to, for plus, the arguments would also be suspended. So we'll have things like suspended 5 or so on. So that we will need to handle, we need to evaluate the arguments of plus again to get the value. So that is eval apply interpreter. It is like a family of mutually recursive functions. If we implement it in F#, of course, it looks very beautiful. If we want to implement it into low-level languages, like if we want to implement it with the languages on the languages without recursion, it would be like we would need to replace recursion by stack. And that's why we can also go in slightly different way, we can try to compile the program into the abstract machine language, which is a low-level language. And the interpretation of this language would be easier. It would not require you to have those kind of recursion capabilities, and you can implement it very effectively using some things like assembly language or so on. So that was important, especially before when people started implementing those things. Also, like with the abstract machines, we do not always deal with the tree, because here with this approach that we have implemented, we always parse this abstract syntax tree, but we can try to break it down into more simple structures which are faster to implement. So abstract machines, they are almost always stack machines. .NET abstract machine is a stack machine because it's very convenient to use stacks for passing arguments to functions. You know that in traditional programming languages, function arguments are implemented as a stack, and also the internal variables are stored on stack. So that is a very traditional way to implement programming languages. So for functional programming languages, traditional type of abstract machine is so-called stacked machine, introduced by Landin first, and it consists of 4 stacks. So S is for stack which we use for calculating expressions. Like, you know that 1 times 2 plus 3, we normally would calculate as putting arguments on stack, and then when we see plus, we do addition. Then there would be another stack E, which is an environment, which is an equivalent of map, which we used for environment in the previous case. Then C is a stack which is called control. It's the current expression which we are evaluating. And D is dump. It is the stack for handling returns from the functions and storing current version of environment when we do function call. So like in real life, when we call a factorial, we store the current address and current mapping of variables into a stack, and then we do the call. So D is for storing those values when we need to return back. So how this happens? Like 1 plus 2, how do we compute it using this stacked machine? So here is the value of 4 stacks. And how they change. So initially, the control stack, which is the current expression for evaluation, would be 1 plus 2. Application of plus to 1 and to 2. Then how do I handle application? I place this special mark, which I represent by this @ to the end of this expression stack. And that's it. And I leave the arguments well in the reverse order. So what this means is that I say I want to evaluate arguments first, and then I will do the application, the actual application. So again, if I see 2, what I do, I put this 2 into the computational stack. So when I see some kind of number, I put it here into the argument stack. So now I want to apply plus to 1. So again, what happens? I put another application psi at the end and reverse the order. So it would be 1 plus apply. So again, when I see 1, I put it into the argument stack. Now I see plus. When I see plus, I put it into stack again because it's the same as constant. And then when I see apply plus 1 2, I apply it partially, so I get this kind of equivalent of operation with partially applied plus. And then when I see another apply, I apply it to 2 and I get the result 3. That may sound a little bit stupid because why do we do those kind of complicated things? It is just to show the machinery of how expressions are calculated. But the most interesting things, of course, happen when we have let and when we have environment. So let's see how we would compute something complicated. So this is lambda f lambda x, f of x applied to suc and 0. So suc is the function plus 1. I just put it like, suppose we have the function for plus 1. So this should give us 2. So suck should be in place of f. It would be suck of 0. So it should give us 2. And lambda f lambda x is the function of 2 variables essentially. So here is the expression itself. I use a for apply and l for lambda. Now we follow the same mechanics as before. When we see apply, we move this to the end of the stack of the expression. Then we see 0. We move 0 to the argument stack. Then we see apply. Again, we move it to the end of the expression. Now we have suck. Suck is the function name, so we move it to the argument list. Now we see lambda. So what happens when we see lambda? In the eval apply interpreter, so this mechanics is pretty much similar to eval apply interpreter, which we implemented before. It is just formulated in terms of stacks for simplicity. So what we did with lambda when we had the eval apply interpreter before, we converted lambda into closure. So this is exactly what happens here. We convert lambda into closure and put it into argument stack as closure. And now we have this apply in the stack. So what needs to happen here is that we need to apply a closure to suck, right, to argument. So how do we handle this in the eval apply interpreter? We call apply, right? So and when we call apply, we calculate the argument of the function and insert into the environment the name of the variable. So this is what happens here when we call this closure. When we want to apply this closure to suck, this closure is with variable f, and the argument is suck. So this is what happens. We put into the environment this mapping, and we evaluate this argument of closure. We put it into the current evaluated expression. And but we need to return back to the current computation stack. So we want to evaluate this expression and then continue calculating what we need to calculate. So here we are currently evaluating application of closure to suck, but we are left with this 0. 0 we need to recalculate later. And we are calculating now this application, but we are left with this remaining application. So that's why we need to store this into the dump stack. So this remaining application goes here, and this remaining 0 goes here. And the environment, current environment, goes here. So dump stack stores the snapshot of the current computation state. It stores the control string, the data, the S stack, and so both 3 other stacks it captures, so that we can return to this later. And now we are focusing on calculating this expression, lambda x f of x, but under the environment that f equals to suck, right? So here we have lambda, so we convert lambda to closure. Unfortunately, you cannot see the end of the slide, but that's what happens here. I'm sorry, it's a little bit small. Let me make it bigger. Oops. So that's what happens here. We put this to closure, but with the environment that f equals to suck. And then we do another call. And we so we have the environment that f equals to suck, and then the expression finishes. So when it finishes, we return everything from this stack, from the dump stack. So we are left to what we are left to compute with is application. Then the result of previous computation is this closure, f of x with the environment of f equals to suck. And we need to apply it to 0. So again, we need now to apply this closure to 0. So we put x equals to 0 into the environment. And we need to compute this application f of x with the environment, with this environment. So we know now that f equals to suck, x equals to 0, and we just need to compute f of x. And this happens exactly as we computed before the value of 1 plus 2, right? Pretty much. So apply is moved to the end, and then we are left with x, f, apply. And then when we, of course, when we say x and we want to put this on stack, we do not put the value on stack. We do not put the variable name on stack. We put the value on stack. So instead of x, we put 0. Instead of f, we put suck, because we know that it equals to suck in this environment. And then 0 suck, 1 suck, and 2. We get the result 2. So that's pretty much how it happens. If we want to implement this, I have the implementation in F#. I don't know if it makes sense to have a look at it. It's a little bit ugly, but again, we have this expression tree, and then we have those stacks. And for each stack, we do one step. You see that this implementation is kind of tail recursive. So it is eval of something, and then this eval ends by another eval always. Like it's purely tail recursive. So it's essentially one loop. And that is the beauty of this stack interpretation, is that we just can do it in one loop. We don't need to handle recursion, proper recursion. Okay, so in this sect machine, we did not consider recursion, but you can try to do recursion using the fixed point combinator. We did not consider how to make this lazy, but it can be handled using the same kind of suspension technique. Any questions so far? I will leave you the code to play with so that you can try to get a little bit better understanding of how this works. But the main thing here is that you, I think what is very important for you to see from this example is that functional programming languages, they allow to define structures which corresponds to any problem domain. So like here, we had the complex domain like lambda calculus or programming language, and we can easily define this kind of abstract syntax tree. And then pretty naturally, we can operate on this structure. So we do not had to worry about like how this would be represented in memory. It was very natural. And that is the beauty of having this algebraic data type system inside the language. Because with algebraic data types, when you have these unions and tuples, you can represent pretty much any problem domain. One more approach is for lazy languages is graph reduction. So in the language, in the Haskell language implementation, we used this approach because the previous approach with suspension operator had one major drawback, which is like if you want to compute something like lambda x 2 plus 2 apply lambda x plus x applied to 2 plus 2, it would be replaced by 2 plus 2 times 2 plus 2, and 2 plus 2 would be computed twice, which is not good. So to overcome this problem, the approach of graph representation was proposed, and there is a book on the implementation of functional programming languages by Simon Peyton Jones, who is one of the authors of Haskell, which describes this approach in detail, how those trees can be represented in memory and so on. But just to give you some examples, like the way those trees work is that if we want to represent something like 1 plus 3, 1 plus 3, we would have this kind of tree. So at would stand for application, and I would say apply plus 1, 3. Then if we want to represent lambda, we would use something like this, lambda with 2 arguments. And if I want to represent something like a list constructor, I would use this one. So let's see how lambda xx plus 1 would be evaluated. So it would be represented by this kind of tree. Then lambda xx plus 1 applied to 2 would be this thing. So essentially what I need to do, I need to, when I call this application, what I do is that I put the reference to this cell 2 instead of x. So I do not substitute the value, I put the reference to the tree. So essentially this node replaces this node here. And why is this important? Because if this argument 2 is not 2, but like if it's an expression, or if x happens, for example, if it's x plus x here and there is another x here, they would point to the same node. And when I need this actual value of x, this tree would be simplified. So it would be simplified once, and because second x also points to the same portion of the tree, it would not be recalculated again. And in fact, when I said tree, it is not properly a tree because it becomes a graph, because if I have those kind of several references pointing to one place, it stops being a tree. So that's pretty much it. There is, of course, a somehow complicated rule of how we do the reduction. Because normally what we do, we consider this leftmost like direction of the tree, and we go and start evaluation from the deepest application on this left portion of the tree. So let's try to see like how this works. X times x applied to 1 plus 2. So this would be the tree. And what we need to do is we need to replace x by this lambda, by this 1 plus 2. And it becomes, as you can see, it becomes a graph. So this is 1 plus 2. And here is this portion of the tree. But those are references like to x, right? And now when I need to do the application, it starts reducing those references. I will not do the more complex example. It's kind of a little bit boring, but you can do that. Here we did not consider how to implement the recursion and how to implement the trees inside the computer. And as I said, the details are in the Simon Peyton Jones book, Implementation of Functional Programming Languages. So in short, trees can be represented by triples, and then we need to do some kind of basic operations on them. There are some other approaches as well, like for example, you can use a kind of flow graphs to represent a flow of computation. So for example, here is the example of how map can be represented as this kind of flow graph. So the map starts with, we say map FL. And this map FL is like if we want to implement map, we would say if L is empty list, then empty list, else map f of x, and this would be the first element, and then the first element f of x, and then the tail would be map of f and tail of x. So this happens here, like the initial list. What we do, we pass it to conditional. We compare it to null. So this says if L equals to null, and in this case if it equals to null, so this corresponds to the empty list, we return the empty list, and otherwise we get the copy. This copy means that we from one stream of data we get two. So this L goes to head and tail. The head of list, we apply function f to the head, and we get this first element. To the tail, we apply this map again recursively, and then we construct from this head and tail the list, and this list is returned. So this is kind of flow graph. If we represent this program as a flow graph, we can kind of pass the values through it and get the results. Okay, of course, we have seen that we have touched on implementation of languages based on lambda calculus, but we have discussed that theoretically it's possible to do everything based on combinatory logic, so on combinators, which would have just one operation of application, and there are specific rules of reduction, so it's possible to view everything as the combinatory logic program, and that's why we can also use abstract machine on top of the combinatory logic. But we would not go and consider many details. I hope you have the general understanding of how a programming language can be implemented. So now if we want to write a complete like interpreter for our own functional programming language, suppose we want to write an interpreter for a language like this. So you want to say let rec fact equals to fun of x if x is less than 1, and here I use, for simplicity, I use dots for apply, so that I don't have to do like complicated expression parsing. So that's why it's like if apply less x1, then I return 1, else I return x times factorial of x minus 1, and then I want to apply this into factorial 5. So this kind of simple. This is the prefix notation, and okay, or I can try to use like infix notation as well. So if we want to implement the language like this, we need to do parsing. Like we need to, from this text, we need to produce the abstract syntax tree. How this can be done? Normally, like if we want to do parsing, we would first write a grammar, something like this. We would say that expression is the application list. Application list is either simple expression or application list and simple expression, and simple expression can be one of those sub-expressions. Traditional approach to parsing things like that is that, well, there are several possible approaches. One of them is that we can do everything manually. We can do the recursive drill down approach when we create a function for parsing. And normally, how do we parse a program like this? Let me go back to the program. So suppose we have something like this sub-expression. So this sub-expression corresponds to some part of syntax tree, right? So it corresponds to like some tree. But when we parse, we do not know like how far the expression could go. So if you want to parse the tree recursively, we normally cannot say, like, we cannot create a function which takes an expression and produces a tree, because we would not know how to break down the original expression into parts to do the recursive call. So normally what we do, we pass the whole text to the function, and we call it, and we ask it, please parse whatever part of this text that you can, and return the rest. So when we do this kind of top-down recursive parsers, this parser function, it takes text as an argument, and it returns a tuple. It returns the tree and remaining part of the text, right? So, for example, let's see how this parsing would work. So suppose I have this let_rec construction. I say let_rec. Let_rec is followed by ID, and then by equals, and then by some kind of text at the end. So what I need to do to parse this, I parse this text T1, and I get the tree TR1 and remaining text. And then I match the remaining text. The remaining text should ideally start with in, because it is always let_rec x equals to something in something. So if my parser parsed T1, it should parse it up to the point of in. And then when I see in, I parse this T2 portion, which goes after in. I get TR2 and remaining text T3. And my tree returns me this let ID equals to TR1 in TR2, and it returns the remaining portion of text T3. If I have this kind of fun x is something, then I parse this text T, and I return lambda ID T and the remaining portion of text R. So I always return the remaining portion of text. If I have the bracket, I parse the thing inside the brackets, and then I expect the remaining portion of the text to start with the closing bracket, because otherwise, I mean, something went wrong. So it's remaining bracket and T1, and I return this T1. So I match the bracket and I kind of eat it from the text. And the same is for like primitive functions. So this is the manual way to parse the tree, which is kind of not very error prone, because here I kind of not considered white space. So I did not skip the white space. For example, here, if before in I had a couple of extra spaces, that would probably not work. So I need to add white space parsing here. I need to, like, it's very difficult to report errors in this case. So it's not the ideal way to do it, but you can do everything manually. And this is one of the approaches that you should probably do in Lab 3 when you are asked to parse the original HTML or XHTML file into the internal representation. So you can manually implement this kind of top-down parser, which is not the funniest thing to do, but it's a good exercise into writing something not trivial in the functional programming language. A second approach is to use automatic generators. This is an approach which has been traditionally used by in producing like normal compilers like C. In C, there are tools called Lex and Yak. Lex for lexical analysis. So lexical analysis is the first step when you convert text into a sequence of tokens. Like here, we did both of those things in one go, but not in a very good way, because here, for example, I just say fun, but what if this keyword can be like, if I want to ignore case, or if I want to, for example, this ID, I do not check if this ID is well formed or not. So ideally, what I want to do the first pass through the text, which will return me the sequence of tokens. And the tokens would have some meanings, like token can be a keyword, token can be identifier, or token can be arithmetic operator. So during this first pass, I want to recognize primary building blocks of the program. And then this is called lexical analysis. And then syntax analysis converts the sequence of tokens into the abstract syntax tree. So traditionally in the Unix world, there are tools called Lex and Yak, and they used to be those tools for F# as well. So they look like this. This is the lexical analysis. You can define like the rules for parsing different things. So for parsing tokens, so it says like let should return the let token. White space should just be ignored. And it says like white space token lexboof, which means that I kind of ignore the white space. I ignore the new line. The ID would be parsed if it's A to Z. If it's a word containing letters, that it would be ID. If it's something containing digits, it will be returned as int. And those kind of operators like arrows, equals, brackets would be also returned as operators. So we can define this, and it would give us the program to do this lexical analysis. So from the grammar, it would give us the program. And the good thing is that this can be written pretty without thinking. It can be written as a state machine, but it's not interesting to write this by hand. So that's why they use program generation. And then for syntax analysis, we pretty much define the grammar. You can see here that I say if it's simple expression, if it's, for example, if, I say if the input looks like if expression, then expression, else expression, I want to return this kind of syntax tree. Cond and $2, $4, $6 corresponds to the argument. $2 is the second argument, so this would be expr, and this would be fourth argument, this would be sixth argument. So pretty much I say here is my input structure. I want to return this part of abstract syntax tree. So from the grammar, we can go to the F# program, which does this whole parsing. So this is not very nice because like code generation is a dirty programming practice, but it works. It's difficult to find errors because once you generated the big, huge, incomprehensible F# program from this, if there is an error there, then it's difficult to figure out where this error lies into the original grammar. Better approach is called combinatory parsing. There is the parser called parsec for Haskell and corresponding F# equivalent called fparsec. And the link you have here. fparsec is called combinatory parser because it is purely functionally implemented. So like it does not do any code generation. It just allows you to combine concepts in the good way so that you end up with the so that your program understands the input text. So the way it works is pretty similar to what we have discussed. So the parser takes the string and it parses as much as it can. So for example, if the way combinatory parser works is that you have the parsers which can parse different constructions. So for example, I can try to define the parser pfloat. In fact, it's probably predefined parser pfloat, which parses floating point number. So if I want to run pfloat on something like 3.14e, it would parse 3.14 and it will return e as the end of as unparsed part of the string. And the real power lies in combining those parsers together. So the way it works is that suppose I want to write something which parses floating point numbers in brackets, like a list of float pointing numbers in brackets. So I can say, okay, let me use strs for parsing the string s. And then one float in brackets, how can it be defined? It is essentially bracket, floating point number, and bracket. But I want from this parser, I don't care about those kind of like opening and closing brackets. I just care about the number. So that's why I use those interesting combinators like greater dot and dot greater. It means combine two parsers, but it would return the value of the parser which is on the same like position where the dot is. So like if I say stir greater dot p float, it would return me the value of p float, and then this dot greater stir, it would return me again the value of p float. So this float in bracket would be able to parse those kind of things, 3.14 in brackets. If I want to return floating point numbers separated by comma, I would say sep by p float and stir comma. It would parse the list of floating point numbers separated by comma. If I want to take white space into account, I would include this white space parser into everything. I would just say float separated by p float, and then instead of just comma, I would say white space, comma, white space. So that's how you can build more complex parsers on top of simpler ones. So if we want to implement the programming language, it would look something like this. I would say I would define this string prime of s, which would be string s followed by white space. It would make it easier to ignore white spaces. Then for idents, there is a special interesting thing. I can say identifier and then pass some kind of options like do we want to ignore case or not, and those kind of things. But we can stick with defaults. Then, because in my case, when I have identifier, I always want to surround it by var from my abstract syntax tree. So that's why I would define this PID, which is identifier, and then passed into the var constructor. Then, if I have let, if I want to parse let, how this would work? I would say pipe 6. It means it would be a pipe of 6 sub parsers, and first one would be let. I would match let, then identifier, then equals, and then in, and then another sub expression. And I want to return let as the result. And that's pretty much for all separate constructions like p lambda, p application, p function, and then at the end, the final expression would be either PID or plet or pin32 or p lambda or p application or p function. And I would be able to parse the expressions like this and return the abstract syntax tree. There is one tricky thing here is that this definition is recursive. So for example, inside let, I want to be able to parse expressions, and expressions I define only later on. So to do that, I use this kind of tricky thing. I say I want to create the parser forwarded reference. So pexpr would be the function which I will define later on. And this reference, I need to assign this reference to the expression at the end. So this is kind of non-functional small thing here. But you can do parsing using this fparsec. You see, it's pretty flexible. So if you choose to do your lab 3 using combinatory parsing, you can also do that. And that would be, by the way, probably easiest way and coolest way to do it. To learn more about fparsec, you can just go to this site and or just Google fparsec, and you will find there is a nice tutorial on how to parse JSON with fparsec. And by looking at this tutorial, you would probably understand a little bit more and be able to do your lab in the cool way. Okay, so what we have achieved so far is that using this approach, we can build parser into abstract syntax tree. From abstract syntax tree, we learned how to build an interpreter. So now we are essentially we have essentially implemented our own simple functional programming language for integers, for integer numbers. Of course, if we want to add some more things like lists, we need to this to be a little bit more complicated. But things like factorials we can already compute. And I think that's pretty cool, because implementing a programming language is traditionally considered a very difficult thing. And you can see that it's very easy to do this difficult thing in functional languages. Well, not very easy, but reasonably easy. So I will share the presentation with you, and I will share the code for eval apply interpreter, and you can play with it a little bit more. So the deadline for lab 3 would be next week, so you can implement parsing in the cool way if you want. And next week I will probably leave you with some pre-recorded lectures to watch on monads, and a week after that, or around that time, we would probably have some kind of midterm check for on functional programming, because we are essentially about, well, not about to finish, but we need to learn monads. And then probably we'll have next week and then the week before next a meeting like this to talk on all the remaining questions, and then we would have the midterm knowledge check on functional programming, which would be multiple choice followed by a problem. And yeah, any questions you have for me? No questions. So I will put the presentation in Teams, and I will put the code sample into GitHub so that you can play with it. Okay, if you don't have any questions, I wish you a great day.
Yeah. I sent 3 questions in chat.
Okay, thanks. Let me check. I don't see the chat because I am from different tenant. Can you maybe, so that I don't relog in, can you maybe either send them in Telegram or just ask in voice?
The first question was about TypeScript, PostScript. Can you tell us about its syntaxes, because we don't understand. I don't understand how it looks like.
Okay, so it's not actually a PostScript. What you need to do? Let me try to find the GitHub. So the idea is that normal PostScript is the language for printers. The idea was that printers can understand some kind of formatting language, but easy to implement in hardware. So this programming language is also stack-based programming language, but it's complicated. So that's why we do not need to deal with real PostScript. It says PostScript-like stack language. So idea is that this language consists of those commands. Like one command is just string in brackets, which means to put string on stack for later use. Then B, I, and N are commands to switch to bold, italic, or normal text. And then P is to print the top string on stack. And then those commands like those signs greater or less, they switch to next or previous level of bulleted item list. So the idea is that, let me give some example. So if I want just to print the string hello, it would be translated into this hello followed by P, print. If I want to print italic string hello, it would be translated to hello, then italic, then P. If I want to print something like hello 1 and then italic 2, it would be translated into hello. It can be translated into different things, but like hello, then let's say 1. Let's say hello, then we move to the next level of bulleted point list. Then I do 1 and print it. Then I do 2. Then I switch to italic. Then I print it. And probably I move back to the, if I want to add some more, then I would move back and then I would say there and print it. And also I would need to switch away from italic as well here. So that would be translated into something like this. Is it more clear now?
I think yes. The next question was about library chart, because I use Visual Studio Code with installed Netcore, and I don't have library chart in my scope at all.
Yeah, that's normal, because this library, you can install it. Let me so you would need to install this. So there are two options, F# charting and Explode, that you can use. They are pretty similar. F# charting is used on Windows. Explode is cross-platform. And the way you install it is that you can do it using NuGet. So I will send you this link, and it tells you like different options on how to install it. You can in Visual Studio Code, you can use NuGet to fetch this .NET package and then reference it from F# using load or using load, and you would have it. So let me send this to the Telegram chat. Or you can two other things you can do. You can go to GitHub. You can go also here to the samples directory, and then open it using binder. So like if you open it here using binder, you would have the notebook which supports charting. It has the sample code. Let me try it. So if you don't want to figure out how to install this library, how to get this library on your machine, you can try to do it in the notebook. And another good way is to install .NET notebooks locally, because that's kind of cool because you can combine. Yeah, I will send you this link as well. So in .NET Notebooks, there are examples which do charting. So it looks like you can use things like Interact IO as well. This takes a little bit too much time to launch, but let's see if it works.
So I ask the third question before it's loading. It's about paragraphs in task 1. If we create them, we never use it in the next tasks. Should we use it or write, or it's not important and we can write task 1 for task 2 and 3?
So the question is about I did not understand correctly. So
we should to create part of data type paragraph, but we never use it in task 2 and 3.
Well, you do, because like if you have the text, you can surround text with a paragraph, like to have it a paragraph of text.
So you mean that paragraphs is something like a string?
Yeah. Well, you don't have to use that. Yeah, but normally it would be nice to be able to separate text into paragraphs. So paragraph is a string which is kind of visually separated. So if you convert it to HTML, you would use p tags, for example.
I understand. Thank you for that.
Let's see. So yeah, here is this notebook has started, and if you go to, for example, notebooks and this intro to Func Pro, this is, by the way, a nice introduction to F#. And if you want to give it to one of your friends who ask you why do you spend time in functional programming course, you can. This is a good place to start. So this thing somewhere towards the end has the example of here. It has the example of plotting the graph. So yeah, I have to run this book. Oops. Let's just try 1, 2, 3, 4 chart bar. Doesn't seem to work. Too bad. Why is that?
So I have a question. If we don't have that library, can we write in the end of program only the chart bar as a instruction, but don't check is it correctly work?
Well, I suggest that you try to figure out how to install the library, because that's not it's not hugely complicated thing. So the idea is that those libraries, they are NuGet packages, like they are .NET libraries, right? And so you should install the .NET library, and then you can reference it in the way like this. If you are completely unable to do so, I would prefer that you write, for example, a text file and then like plot it in Excel or something like this, so that you can replicate the whole process. I don't want you to like just write the code which you cannot execute. I mean, that doesn't make a lot of sense. So you can like graph it using GNU-plot, or you can graph it in Excel, but it's definitely easier to figure out how to do it in F#. It's kind of engineering exercise which is not too complex, and like everything is described in the links that I shown you. Let's try, for example, this Interact IO. should have the before, there used to be a very good thing called Asia notebooks, which contained like everything. No, Interact.io seems to be downloadable. You need to download something. That's not cool. So let's do that. Try to figure out how to install it. If you are completely not able to, write in Telegram, and like maybe some of your friends would be able to help you. Like everybody is facing the same problem. Just maybe you can try to fix it together. If you are completely unable to, I will jump in and I will give you some like. Okay.
Thank you.
Thank you. Okay, I hope. I mean, if there are any other questions, please ask them. If you have the questions you don't want to ask by voice, but you want to ask in the chat, write in Telegram. And if there are no questions, then have a great day.